So, hello. Today we're gonna talk about the difference between the Prim's algorithm and the Dijkstra algorithm. So, you, assuming you have gone through them in lecture, they might sound very different. They achieve very different tasks. The Prim's algorithm generates a minimum spanning tree, while the Dijkstra's algorithm gives you the shortest distance away from your starting point. So it's a single source shortest path. Yeah. Uh, but in fact, they're very similar algorithm. And I will demonstrate with this graph that I think there's only one difference between the algorithms. And if you write it out in code, the difference will be like one or two lines at most. And if you learn the difference as well, maybe you can save some space on your exams cheat sheet because you don't have to copy both algorithms code or any other pseudo code or steps like that. So take a look at this graph. Let's set A as our starting point. Let's try to build an MST with the plane first. And yeah, let's actually do both algorithms at the same time. So for both, we the first step is always similar. You you just added the shortest edge that's away leading away from A, which in this case is AB. So the next one to insert into the MST or the shortest path, the digester result is going to be B. But here is the where the distinction comes. So MST, we want to add the edge that's closest to um, our tree. We want the goal is to connect all the nodes together with minimal distance, not to get to any node the fastest. That's a very important distinction. So right now, how we compute the distance is that C is 3 away from our tree, and D is D is 2 away from our tree. So we're we're choosing to add D because it's closer to our tree. So this way we can build the smallest tree, the minimal spanning tree. However, the digester, which I don't know how to spell it, um, we want the shortest distance from the starting point. Well, if we want to right now, we can reach both C and D. If we compute the distance of D to our starting point, you will see it's 2 plus 2 is 4. And if you compute the distance from C to our starting point, you can see it's 3. So in this case, we should add a smaller one. That will be C. And then there's only one node left. So both algorithms gonna add the same. So you can see this does generate the minimum spanning tree. So it's gonna include this edge, and this edge, and that add to 5. And if we somehow want to include this edge in any way, you will see that the tree becomes bigger, and that's incorrect. At the same time, the shortest path tree included this edge, and this edge. Sorry, the arrow should. And you can see that there might be more than one correct way to find the shortest path. In fact, no matter which side you choose, you can always get to D with a distance of 4. But with our algorithm, we decided to use this edge because we can get faster to C using this edge. If we do not include this edge, A from A to C is going to take a distance of 5, and that's also incorrect. So although this distance to D might be correct, no, if we choose the alternative route, distance to C will not be correct. So to get to anywhere from C, we just see what edge. I mean, to get to anywhere from A, we just see what edge is included. For example, you want to get to B, you take this included edge, and it should also be a tree that there's no loop. You cannot get to B from the other side, and similarly get C. We talked about this before. Get to C, choose the edge AC, and get to D, choose AB then BD.